Good evening. My I'm going to present on the topic signal reconstruction using neural networks. So first, I'm going to break down the title. The first thing in the title is signal reconstruction. So what do I mean by signal reconstruction? In signal processing, reconstruction usually means the determination of original signal or expected signal from a sequence of samples. What does this mean? So, for example, if we have a sequence of numbers, sequence of data that is somehow related to each other through some equation, but we don't know what the equation is. What I'm going to do is feed this data into a neural network. The neural network will learn how the data is related to each other, and then perform extrapolation on the unknown values of the data and give us the original graph that was supposed to be in the we were supposed to get in the first place. So the second thing that I'm going to talk about is the neural networks, the thing that I'm going to use to demonstrate this ability. Neural networks are neural networks or artificial neural networks are computing systems that perform tasks by considering examples without being explicitly programmed to do so. What does this mean is that there are certain tasks that computers can perform without being explicitly programmed to do so. For example, recognizing a face. So, recognizing a face requires computer to uh, we can't program this kind of ability into computers using classical methods. We can't hard program computers into recognizing someone else's face because there are always certain parameters that doesn't match up if we take the two photographs of the same person. But computers using neural networks have this capability that they can use probabilistic methods to determine that whether that person is the same as in the picture with to some degree of uh, accuracy. Renans are directed weighted computational graphs. What does this mean is that they have a certain direction in which computation occurs. Each node in the graph performs some computation on the input, and then it exerts its influence as a number which is called weight. It learns by examining the difference of the given output and the training. First of all, we divide the data set into two parts, that is the training set and the test set. So we use a training set to micro adjust the parameters that computes and give the output. How this is done is that we have the output, we observe the differences in the given output, and then use the difference to adjust the parameters that compute that works in neural networks. So this is the diagram. As you can see, I have there are three layers. So first layer is the input layer, and the last layer is the output layer. There is no computation done in those layers. These are just for this, these are just placeholders for data to input and output. The main computation that occurs in is in the middle layers or the hidden layers. Here I have only drawn one, but there can be multiple. So how does neural networks perform its calculations? So each circle in the graph represents a processing unit. What does this mean? That these units receives data, they perform calculations. Every unit has a state of activation. What does this mean is that for certain values of the data that is fed into the units, it will perform some calculations. For some, it won't. This is analogous to the firing of neurons in our body. So, as you can see here, connection within the systems is I have as I've shown with arrows the connection between two units. So when data is being transferred from one unit to the other, the arrow represents the influence of the preceding unit. How much influence does that unit have on the overall input that is being fed into the succeeding output? As you can see in the first circle here, the data is coming from all three input layers. So for example, let's say we have W1 weight for the first one, W2 for the second, and W3 for the third, and the output is A1, A2, A3. So the input that the first unit will get is A1 W1 plus A2 W2 plus A3 W3. So W1, W3, and W2 and W3 represents the influence of the preceding units. Next is associated with uh, each succeeding unit, there is a bias or offset. So, for example, the computation is done. Now we have an output from the hidden layers, and it is now moving on to the second layer of the hidden layers. So how does that output changes when it goes from one to another? First is we multiply it by weight, but uh, because of certain differences, certain mathematical consideration, we usually provide certain offset to each output when it moves to the other unit. This output is called bias of the succeeding unit. Now we define a propagation rule for each unit that determines the overall output of the system. What this propagation rule is, that usually we define a function, if the function that takes the input and decides whether the neuron will fire, whether the unit will perform calculation or neuron will fire. So as a learning rule as a whole is defined, a learning rule is as a whole is defined for the graph. For example, like how do we determine that the ANNs are performing calculation as we need them? So for this we usually define excuse me, for this we usually define a cost function. Cost function is the measure of the error that that is this cost function is what we are going to reduce, or we are going to minimize that error between the output and the input as much as possible. So these are you. This problem usually lies in the area of calculus of variations, and there is a algorithm called stochastic gradient descent that helps us. How this works is in a in like for in two dimensions. If we have a simple Gaussian curve, and we want to find we want to find the maximum, for example we have an inverse Gaussian curve, sorry, we have an inverse Gaussian curve. We want to find the minimum. We take any point on the curve and we observe the slope. Now we move in the opposite direction of the slope. Eventually we will find the minimum of the curve. Now, this minimum is not necessarily the global minimum, it could be local minimum, but what we need is to reduce the error as much as possible. Our job is not to find the global minimum, but to find a minimum so that the solution is stable. So after one computation is done, we need to adjust the parameters of the unit so that error reduction is propagated through further calculations. This is usually done using algorithm called backpropagation. What how does this work is, after the calculation is done, each parameter, each unit and its influence or the bias that it has is reset recursively. So each and every unit is visited once, and each and every unit is made sure that the algorithm makes sure that the bias and the weights of the processing units are set up according to the proper calculations. After repetitive calculations, we obtain the result. So our aim in my aim in this presentation was to demonstrate that neural networks can be used to study and analyze sequential data. So for to analyze sequential data, we must have a concept of memory in whatever system that we are using to analyze. Because in sequential data, the preceding and the succeeding data are related to each other through some relation. Now, normal artificial neural networks don't have this capability. They don't have the capability to have some memory, uh, as we use in neural network terms. They don't have memory. Okay, they can't relate data from preceding and succeeding inputs. But there is a certain kind of neural networks that was developed to tackle this problem. These are called recurrent neural networks, and this is what I've used to demonstrate this for this demonstration. Our aim was to reconstruct the signal. For this purpose, I have used RNNs. The memory capability that is implemented in a neural network or in the RNNs are done by a feedback loop. So, for example, for example of a RNN in human body, also if one person looks at a light bulb for a certain time or the sun for a certain time, then close his eyes, then there's a certain bright hue in his vision, even if everything goes black. So even inside our brain, there's the network that we have, the synapses that we, the neurons that we have. It remembers data which is being fed, and it produces output based on that data. That's why we see a bright hue even after we close our eyes. Similar kind of thinking was used to develop this. So as we can see here, there's a feedback loop from the processing layer back to it. So this feedback loops give the RNNs capability to have memory. How this is done? So simple, we this if we consider this as a whole unit, and we define batches what for the RNNs, meaning how many data in parallel are we going to feed into the system. So my demonstration consists of four parts. First is the constructing the input signal. This is done using Fourier series. I've constructed very simple signal using four sinusoidal waves, superimposing four sinusoidal waves. Second is training the RNN on the generated data. I have created around 50,000 instances of different points and calculated the values for them to train the data. Then we have to calibrate the hyperparameters of the RN for maximum accuracy and fast conversion. What I mean by this is that there are certain things involved in training neural networks, like how many times does the neural network have to go over the whole data set or epoch, batch size of the RNN, how much data are we going to feed it in parallel, these things, and what kind of cost function are we going to use, what kind of the convergence rule we going to use. These things determine how fast the RNN uh, reconstruct the data or we find the result. So as you can see is after 50 each epoch usually means that uh, one epoch means that we go over the whole data set one time, and after each epoch I reshuffle the data, and then another run is done. So after 50 epochs we can see the RNN didn't really reconstruct the data, it didn't really learn much, but we can see the trend is reconstructed. After 100 epochs, we can see that it can sort of understand what is the relation between different data set, but it hasn't been able to done the fine tuning. After 150 epoch, we can see that the RNN finally realized the original underlying relation, and it can predict the original signal pretty accurately. Observations. We can see the neural networks are highly capable in RNNs are highly capable in recognizing and remembering sequential data information. By adjusting the hyperparameters, we can ensure even faster convergence of the process. There is limitless applications of this kind of thing, especially in signal processing, signal analysis fields. Like for example, medicine. Real-time heart blood pressure data can be acquired, and using neural networks we can predict. Researchers have been trying to predict heart attacks before they happen. This is like smartwatches. Nowadays the companies are developing smartwatches that record real-time blood pressure data. So using that we can predict heart attacks, because we can train models to recognize when a heart attack is going to come. So it detects the pattern, the signal of the signal of the blood pressure, and can recognize whether the conditions are or not. So it could be very, very beneficial for us. Astronomy is another field. In astronomy we record spectrum of different radiations that from celestial bodies, and now that we have very sophisticated instruments and telescopes, so the data that is acquired is increasing day by day. It is not possible for humans to uh, manually check the data, so more machine learning, deep learning, and statistical methods are being developed to find the patterns and relations that is not obvious to us humans, but computers can find them. And this kind of things, neural networks can be used to do that. Data recovery is another field. As I've shown, signal reconstruction can be done using RNNs. Data recovery can also be done. For example, certain satellites have redundancy programs in them that in case of failure would reconstruct signals with broken data. So certain similar kind of systems are used in them. Meteorology is another field where probabilistic learning is making headways. Based on humidity information and wind pressure and speed, one can determine whether a hurricane is going to hit or not. What is going to be its impact? So many different limitless applications can be thought of using this. Thank you very much. That was.